Okay, so the purpose of this talk is to give you some general comments about the PAT, the format of the PAT, and how might be the best way to prepare. Outside there is a leaflet which says preparing for the physics aptitude test. What I'm going to talk about is basically on this sheet, but I'll go through some of the resources like past papers, the syllabus, explain a bit about what we're looking for, and you're going to do some past paper questions. You're here in a physics department, you must want to do some maths today. So we will do some past paper questions together, and then I'll mention some other resources you could use and conclude. So the general comments are that if you apply to Oxford to do physics, physics and philosophy, material science or engineering, you must take the PAT. The PAT is hard. It is not like any other exam you probably will ever take. Less than 1% of the students get between 90 and 100 marks. You are probably all amazing people and you've never scored less than 90 in your life. That is not this sort of test, okay? If everybody got 90%, it would be no use to us. So, you know, it is quite a hard test. So that means don't be discouraged if you see hard questions. All right, we have to put a range of questions on in order to discriminate between a very able cohort who are applying for our degrees. You do need to develop a strategy on how you're going to tackle this paper. Are you going to try some questions first and come back to others later? Are you just going to start at question 1 and work all the way through? You do need a bit of a strategy for this. So the format of the PAT is that it is 2 hours long. There is a mixture of maths, which are worth 50 marks, and physics, which is worth 50 marks. If you look at past papers over the last 12 years, you will see that the rubric, the actual layout of the paper has changed, and the current rubric is that you will have 6 maths multiple choice questions. Each multiple choice question is worth 2 marks. 6 physics multiple choice questions, and each of those is worth 2 marks. And then a selection of higher mark questions on physics and maths. They might be anywhere between 3 marks and 10 marks, and the questions are mixed up. So there might be a maths question, then a physics question, then another physics question, then a maths question. The reason for this was that we used to have the maths at the beginning and the physics at the end. People never got to the physics. It's, you know, we are asking you to do a physics test. We would like you to do some physics questions. That's why we mix them up. Question?
So by saying that, I assume you don't expect everyone to actually finish the test.
We would like you to finish the test, but it is quite common that people run out of time. They don't have a good strategy, and they then run out of time, and they don't make it to the end. And that was a bit of a problem, especially if the longer questions tend to be towards the end. So this is why you need a strategy. Okay? So we asked our current students, how did they prepare for the PAT? So these are people who are physics, engineering, or material science. They took the PAT, they had an interview, they are now our undergraduates. And we said, okay, how did you prepare? The most useful thing that people said they did was they did some past papers. The style of questions is a bit different to A-levels, so by doing some of the past papers, it meant that they kind of were a little bit more familiar with it. Check the syllabus. We do publish on our website the syllabus. I will mention in a minute the sort of material we try and cover. There may be things you might need to teach yourself for reasons I will go into. You need to do some other problem-solving type questions, so things like physics Olympiad questions, Isaac physics questions. These are all good resources, they are free, and you can use them to practice doing problem solving. And do some of the questions under timed conditions. When we asked the students, what was the hardest thing you found? They said, we ran out of time. So making sure you can do things in the time we set is really important. The other thing was the style of the question. The style of question is often different to A-levels, and that can also be a bit of a challenge if you've never looked at that kind of question before. What was interesting to us was only 25% of the people who replied to our survey actually had a regular PAT preparation club in their school, and over 35% did all of the preparation themselves. So this means if you're at a school where maybe you're the only person applying, your school cannot offer support, that is not a problem. If you are motivated and you are prepared to sit and do some problems yourself, you can succeed, and you would probably then do very well on our course. So you don't have to have a regular club in your school. Question?
Do you think it's useful to do the past papers from the old syllabus?
The syllabus has not changed radically over the last 12 years. So we do have 12 years worth of papers that are on our website, and the syllabus, we may have taken a few things off, but otherwise we haven't changed the syllabus to a large extent. Question? That one I don't know, but probably not necessarily. I've known some people who have done all the preparation themselves. They've done amazingly well on the test. Okay? So you can do it. If you are motivated, you can prepare yourself. So in terms of the past papers, these are available online on our website. If you go to our website and there's a study here, and underneath applications we have physics past papers, and there's a very long list. For every year there is a paper and there is also a report. The report says what the mark was that was needed that year in order to get an interview. What we have found is that people who do well on our course do well in the PAT. So we have a mark that we set, and that mark is chosen so that every year we interview roughly the same number of people, around 500. So if the paper was very easy, you might need a higher mark that year than if the paper was very hard. So there is no such thing as a pass mark. Okay? It depends how you do relative to the rest of the cohort taking that paper. Now that is how physics use the PAT. If you're applying to engineering or material science, they use it in a slightly different way because they combine it with things off the UCAS form. Those are subjects where you're not doing those at A-level. You have to write something to say you really do understand what material science or engineering are. Okay? So it's not just what you get in the PAT for those subjects. So in the 2017 paper, the last year, the average was 52 plus or minus 14, and everyone who scored 59 and above was offered an interview for physics or physics and philosophy. There were 87 people who achieved below that, and they were also invited for interview, and that gave us a grand total of 530. That's one of the largest cohorts we've ever interviewed. All this information, I don't know it because I work here, it's in the report. Okay, so that's the sort of information which is in the report. Okay, so past papers. There is only one set of solutions on our website, which is for the 2009 paper, but we do know that solutions do exist on the internet. They are not our solution, okay? So we haven't gone through, we haven't checked that they definitely work and that they're definitely the correct answer, but we would hope that they would be the correct answer. So solutions are out there, but they are not necessarily ours. The reason we don't give you solutions is because we don't want you to get really worked up about, I have to do it this precise way. If you answer the question correctly by any method, you will get the marks. And what is really important is that you write down your working, because you might be doing a completely different method to everybody else, and maybe you just made a little slip somewhere. You would get some marks for that, okay? So it's really important that you do write down what your thinking is. But we don't want you to think that you have to do it a specific way. If you get the answer by any method, that's fine. Okay? The syllabus, we try to cover first year maths and first year physics A-level. It's probably useful if you do some preparation this summer. You know, you've got a nice quiet summer before you start your last year at school. And so you've got some time. And it is quite important that you do think about this early. If you haven't covered some of the syllabus, please do ask your teachers. The syllabus, because A-levels have now moved to linear A-levels, schools might teach things in different orders. So we can't guarantee that things we have on our syllabus you will have been taught. We hope they will have been taught, but we can't guarantee it because your school might teach things in a slightly different order. It is also possible some of the things your teachers are planning to cover in September. So it's worth checking with them before you break up for the summer. Will any of this material be covered in September, or are there things I need to teach myself? We will not give you a formula sheet. There are some equations we expect you to know. But this year we will allow non-graphical calculators. So outside there is a sheet which tells you all about the specification for calculators. Really it's a calculator which is very basic. We're allowing it not because we're putting in extra hard calculator questions, but because some people they spent so long trying to multiply two numbers together. That isn't a good use of testing whether or not you can do physics. Okay? So that's why we're allowing calculators. Okay? It doesn't mean it's suddenly got massively harder. So the syllabus, unfortunately, it doesn't show up very well on the screen, but it is on our website. So again, if you go to Physics Aptitude Test under Applications, you find the PAT syllabus. This has been updated recently, not because we've made it massively bigger, but because we've tried to be a bit clearer about what we expect you to know for each topic. We've tried to break the topics up a bit more. Okay, so that's what maths looks like. And it has basically some elementary maths, some algebra, and some calculus. The physics looks like it's got massively longer, but it hasn't. We've put in things, for instance, kinetic energy is a half mv squared. That's an equation we expect you to know. Another example was in the natural world. It was basic knowledge of bodies in our solar system. So before, it just said knowledge of the solar system, and some teachers and students said, well, that's a bit vague, we don't know what that means. So we've said basic knowledge of bodies in our solar system, including planets, moons, comets, and asteroids. Name and relative position of the planets should be known, but detailed knowledge of the physical parameters is not required. So we do expect you to know what a planet is and the order of them, Jupiter, Saturn, that kind of thing. We don't expect you to know what a Jovian day is. We don't expect you to know how many moons Saturn has got this week. But we do expect you to know there are planets. If there was a question that said there is an asteroid, you would have a vague idea of what an asteroid is, okay? But not really detailed knowledge of the typical size or anything like that. Just you do understand it's basically rock. That's the important thing. Okay, so that's why it may look longer, but it's just to try and help you. Okay. So what are we looking for with the PAT? We're looking for whether you can do the basics. Okay, there are some basic bits of maths we need you to be able to do, because if you can't do them, you would struggle on our course. Can you think about the answer you've got? So it might be that a question says, calculate all of this for red light. What happens if now you've got green light? Okay, so you've got to think about the answer a bit. Can you use new information we give you within a question? This is a common thing we ask in interviews as well. We might give you something, you'll never have seen it, that's fine. All the information you need is in the question. Can you pick it up and run with it? Because that, again, is a skill we need our students to have. Can you express a question in terms of mathematical expressions? Our course is so mathematical. As someone who tutors maths to undergrads, it is very, very mathematical. And so it's really important you have the skills to take a question, decode it, put some letters on it, and turn it into some maths. Okay, so that's the sort of skills we're looking for. Right, so now you get to do some maths, okay? Parents in the audience, you feel free to join in. I know those, if there are any sitting in the Lindemann, the blackboard doesn't come across very well, but we'll give it a go. Okay, so all of these questions are from the 2006 PAT paper. Okay, so we'll start off with some maths, all right? So can you do some of the basics? So the question says, sketch the functions sine squared of x and 1 over x squared minus 1. So have a few minutes to try those questions. Okay, so for our first function, y equals sine squared of x. So there are various ways that I could sketch this graph. I could differentiate it, I could find turning points, but that seems a bit complicated. Perhaps I'll start with something a little simpler. I might just start with the function y equals sine of x. I would, of course, remember that that is 0 at 0 degrees. It's 0 at 180 degrees. And it's 0 at 360 degrees. And then at 90, it has the value of 1. And at 270, it has the value of -1. And I'll draw that diagram. And then to work out sine squared, I just need to now square my function. So the zeros are still going to be there. 0 squared does give me 0. If I square 1, I will still get 1. If I square -1, though, now I'll get 1. And so that I'm expecting a nice smooth function. So that would be the graph I would be expecting. Does that make sense? Everyone got that? Cool. You can do this. Great. Okay. So y equals 1 over x squared minus 1. Again, I could differentiate it and find turning points. I could take limits as x became very large or very small. But I could also do it by saying, okay, let's do some translations on a function. So I could just say y equals x squared and plot that. Hopefully we can all plot a parabola. I could then say, okay, y equals x squared minus 1. So that's the same graph, but it's now shifted down to -1. And then I could say, okay, now I need the inverse of that function. So wherever I had a 0, that will now become a vertical asymptote. And this one would also give me a vertical asymptote. So -1 and 1. Y equals 1 over x squared minus 1. If the function is negative, doing the inverse of it, it's not going to change its sign. So that means this bit's got to be negative. From 1 onwards, that would have to be positive. And from -1 to -infinity, that would also have to be positive. Okay. If I do 1 over -1, I would expect to get -1. But if I now do 1 over anywhere between 0 and -1, that will become a bigger number. So that's going to go down. And from 1 onwards, 1 over x squared minus 1 becomes very large. So that would become very small. And that would become very small. Okay? So that would be the graph I would expect. So sketching graphs is a common question that we set. It's also a common thing we ask in interviews. So you should have a strategy, all right? And you can do it as shifting and scaling. You can do it as, doing differentiation and limits. And either of those is going to work, and either of those is going to be fine. Okay? That makes sense? Cool. Okay. So now we'll do this one. This one is a harder question, I warn you now. Okay? So this question says, in the figure below, the radius of the larger circle is twice that of the smaller circle. Find an expression for the fraction of the area of the square which is occupied by the two circles. Okay? So this is a question, it gives you no letters for anything. Okay? You're going to have to invent some. So have a go at this one. Okay, so this is quite a hard question, all right? The one thing I'm going to do to my diagram is I'm going to do a line that goes through the diagonal of the square. The reason for this will become obvious in a little bit. So I need to invent some letters. So I'm going to say that the radius of the smaller circle is r. So the radius of the larger circle is 2r. And I'm going to say that the side of the square is a. I can call it any letter I want, doesn't matter. Okay? So, the area of the circles, hopefully you can all remember the formula for the area of a circle. So I have pi r squared plus pi 2r all squared, so that would be 5 pi r squared. And the area of the square, that would be a squared. So you can all remember this. Yeah? This is all okay. So even if you just write that down, that might get you a mark or so. Okay, so that's useful. Right, so now what we need to do is we need to relate r and a. Because we want the fraction, so we need to kind of do 5 pi r squared divided by a squared, but we need to get rid of r and a, these letters we've invented. So, the length of the diagonal would be equal to root 2 of a. If it's a squared along here and a squared along there, that bit by Pythagoras would be the square root of 2a. Then we will split our line into segments. So this length here must be 2r. It's the radius of the larger circle. That one there must be r. It's the radius of the smaller circle. So then we just have these bits that go from the center of the circle out to the corner. Now this length here of this triangle I've constructed must be equal to r. The height of the triangle must be equal to r. So that means that this length of the diagonal is root 2r, again by Pythagoras. So similarly, this length across here would be 2r. It's the diameter of the radius of the circle. That one is 2r as well. That's also the radius of the circle. So that length is 2 root 2r. Okay. So what we've now got is two formulae for the same length. So root 2 of a is equal to 2 root 2 of r plus 2r plus another r plus root 2 of r. Okay? And that would give us 3r 1 plus root 2. So now we've got a relationship between a and r. So the fraction that we're looking for, which is 5 pi r squared divided by a squared, that will be equal to 5 pi r squared divided by 3r over root 2, 1 plus root 2 all squared, which if we simplify a bit will give us 10 pi r squared over 9 r squared 1 plus root 2 squared. So that's 10 pi over 9 1 plus root 2 squared. So that's not a nice simple number, is it? No. Okay, but that is what the answer is. All right? So that's what we mean by, we might take something you have done, like areas of squares and areas of circles, but you end up with something just a bit harder, we push it a bit more. Okay? But even if you've got somewhere along the lines, you would get some of the marks. Okay? But that's one of the more challenging questions. Okay? Right. Okay, so that was some maths. Let's do some physics. We need to do some physics. Okay, let's try this one. So this is a multiple choice question. I can do a show of hands on this one. So this one says, a block of niobium and metal with density 8,570 kilograms per meter cubed has sides of length 3 centimeters, 4 centimeters, and 5 centimeters. What is the maximum pressure that can be exerted by this block when it is stood upright on one of its faces. Okay. So this is a multiple choice question, so you don't get long to spend on it. Okay, so as it's a multiple choice question, you don't get long. Can I have a show of hands if you think the answer is 4.3 kilopascals? Can I have a show of hands if you think the answer is 430 pascals? A few. 2.6 kilopascals? 510 kilopascals? A few. So the rest of you, you've just not decided on anything yet. Okay. The actual answer is A. It is 4.3 kilopascals. So the sort of equations you're going to need for this one is you're going to need pressure is force over area. So that's mg, the weight, divided by the area. A diagram might be helpful. I'm a big fan of diagrams. In order to get the highest pressure, you need the smallest area. So this one is going to be 3 centimeters by 4 centimeters. However, these are in units that are different to the ones for the mass, because that's going to be density times volume. And the density was given in kilograms per meter cubed. So notice, we try and do that sneaky thing they do at A-level of mixing up units, all right? But the answer is indeed A, 4.3 kilopascals. At the time that people were sitting this paper, they had no calculator. You would now have a calculator. So take pity on those who had to do this. Okay. Right, so another multiple choice question. A Martian. A Martian attempts to measure his mass using a set of bathroom scales in his house on Mars and gets a reading of 93 kilograms. Unfortunately, his scales were designed for use on Venus. Given that the gravitational strengths at the surface of Mars and Venus are 3.8 newtons per kilogram and 8.8 newtons per kilogram respectively, what is his true mass? Okay, let's have a show of hands. Try and pick one of these options. Okay, show of hands if you think the answer is A, 40 kilograms. Some of you, a few. Okay. Answer B, 106 kilograms. No one's taking that one. C, 215. That's a bit more popular. Or D, 245. No, the answer is indeed C, 215. The number that you need to have calculated was 93 times 8.8 divided by 3.8. You would like to find the weight that was measured, which needs the 8.8, but you want to find it on Venus. Oh, sorry, on Mars. So it's divide by 3.8. So the answer is C, okay? Right, circuits. You all love circuits? See, yesterday everyone went, oh, circuits, right. Okay, so circuit diagram. The diagram below shows a circuit in which the bulb lights up with normal brightness. So you do have to understand what those symbols mean. In the circuits below, the bulbs and cells all have the same specifications as the bulb and cells shown above. Determine whether the bulbs marked by the letters in these circuits are brighter than normal, normal, dimmer than normal, or off. Okay, so there's like A to H, and you just have to say whether you think they're brighter, normal, dimmer, or off. Some equations, you might use some equations, you might not. This question obviously gives you no values for resistances or voltages. You can always make some up if you needed to in order to make your, if that helps you. Or you can just reason it out. Okay? Okay, there's a bit of discussion, a bit of puzzlement, but surely there's confidence. Be confident, that's the thing. Okay, so for the first circuit, we have lamp A. Can I have a show of hands if you think it is brighter than normal? Do you think it's normal brightness? Do you think it's dimmer? Yay, we can do this. There we go. Right, okay. So what about B? Okay, do we think B is brighter? Do we think it's normal? Do we think it's dimmer? Do we think it's off? No, see, you're fine. Yes, it's normal brightness because you have two cells for two bulbs. Okay, how about C? Do we think C is brighter? One person thinks it's brighter. Normal? Yeah, some. Dimmer? Some. Off? Nobody's gone for off. This one is normal brightness. There are 2 cells and 2 bulbs. If you look at the loop which goes around the outside, you've got 2 cells and 2 bulbs. So that would be normal brightness. Okay, how about D then? Is D brighter? One person thinks brighter. Normal? Some? Dimmer? That's looking more popular. Off? Off is correct. Okay, it's off because there is no potential difference between those 2 points. You need a potential difference for current to flow. So D is indeed off. Okay. E. Right, E. Do we think E is brighter? Do we think it is normal brightness? Do we think it's dimmer? That's looking more promising. Off? Yes, dimmer. Because we've got 1 cell and 2 bulbs, so it's the same as A, basically. Okay, how about F? Do we think this F is brighter? Think it's normal? Dimmer? Few? Off? It is actually normal brightness, because if you go round the first loop that goes through F, you've got 1 cell and 1 bulb. Okay. Right, so the last 2. Okay, so G. Do we think G is brighter? Some of you are thinking brighter. Normal? The odd couple normal. Dimmer? Off? So you're thinking off. It's actually brighter. If you go around the outside, you've got 2 cells and 1 bulb. So therefore, that one would be brighter. And you could almost look at that and think, we have not had a brighter one yet, have we? So, must be a brighter somewhere, surely. Okay. H, last one. Do we think that's brighter? Do we think it's normal brightness? Some of you. Do we think it's dimmer? Some. Do we think it's off? Some think it's off. No, it's normal brightness. It can go that way. That's fine. So you could kind of go round through 1 bulb, through the second bulb, and then it looks exactly the same as for B. Okay? So that's H. Okay? Right, so that was some circuits. So again, you could do that by plugging in some numbers. You could do it by reasoning it out. It's always a fun one, that. Yes?
You haven't actually written any explanations then. You could do a table like that.
You could do a table like that, and that's absolutely fine. Yeah? So you don't need to have done any calculations. You can just write a table in that case. Yes?
Going back to the multiple choice numbers, would we be expected to estimate those numbers about that, or would we be expected to do the long on a piece of paper?
You can do any way you want as long as you come to a number. So if you do it in your head, great. If you do it on a calculator, now we're giving you a calculator, that's fine. Okay? Any other questions on those? Cool. Okay, I think we'll finish with the questions for that. Just to give you some ideas of some other resources which are listed on the sheet. British Physics Olympiad, their website is very useful. It has questions by topic. It has solutions to all of those questions. So that might be helpful to you. I want to study engineering. You don't have to be wanting to study engineering to use this website because it has some nice maths questions and physics questions, so that's all fine. So there is some advice on bits on the sheet. Yes? No. No. Okay, so that's I want to study engineering. Could I just have 2 more minutes of your time? There we go. Right. Isaac Physics. If you've not come across Isaac Physics before, there are some postcards out the front. This website was specifically designed to improve students' problem-solving skills. And when I was looking at this, I found some questions which could almost be taken off the pat. That web address, I think, is not on the sheet. Okay? But these are questions that I just found. I thought they looked like pat questions. I grouped them together. But there are many other questions on Isaac Physics which are of the right sort of complexity. You probably want to be looking for about level 4, level 5 kind of questions. That's the sort of level of difficulty for the more challenging questions. But we do usually put in some questions which are a bit easier as well. Okay. So to conclude, to prepare for the PAT, we really recommend you practice with some past papers, that you check the syllabus, you use other resources, don't just use A-level questions. You need to use a bigger spread of problem-solving questions. Don't expect to get everything right on this paper. It's a hard paper, and people rarely get 90 and above. But try and make sure you get to the end. So have a good strategy for how you're going to tackle this paper. Right, do you have